In the mid-20th century, millions of pregnant women were prescribed with a drug that was believed to be safe, effective, and evidence-based, but it was none of those. Diethylstilbestrol, or DES, was approved in 1947 and promoted for decades to prevent miscarriage, despite some trials in 1953 showing that there was no benefit at all. What followed was a medical tragedy, unfolded slowly and brutally. DES remained in widespread use through until 1960s. In 1971, researchers linked DES exposure to a rare cancer in young women. But by then, the damage was multigenerational. What failed here was the method used for statistical experimentation and inference. The DES tragedy is a statistical lesson that stands as a stark reminder of why good design of experiments are crucial and a foundation for making reliable conclusions about a study or an experiment. Hi, welcome back to Lankers. This is the episode 1 of our series on statistics. In this episode, you will get an introduction to statistics and specifically the design of experiments for statistical analysis. What is statistics really? Statistics is the art of making numerical speculations about puzzling questions. For example, what is the effect of a new medical treatment, a new drug? How casinos make profit at roulette? Who wins next election and by how much margin? These are very difficult issues, very difficult questions. And statistical method helps a lot if you want to think about these sort of questions. These are the methods that have been developed over several hundred years and by people who were looking for answers to these sort of puzzling questions. So in this series on statistics, we cover the core toolkit for statistical analysis and reasoning. First, in this episode, we introduce design of experiments, the foundation for the statistical analysis. You will learn what is good design and how it helps to make reliable conclusions from your data. Also, you will see examples of bad design of experiments with some case studies. So you see the pitfalls and some real case studies where bad or poorly designed statistical experimentation lead to wrong conclusions. You will see why design of the experiment is the foundation, because data collected from an experiment is only as good as the method used to collect this data. So this is very important, the foundation for any statistical reasoning and statistical analysis. Then we will cover descriptive statistics. So studies, any study, experiment, or trial produce so many numbers. So we need some summaries about these numbers so we can make conclusion, make sense of these large number of data that we collected from our studies. That is what we call descriptive statistics. It's the art of summarizing a big chunk of data into meaningful, forms of information. You will learn about histograms, the average, the standard deviation, and the normal curve. These are the core concepts, the core ideas of descriptive statistics. You will also learn about how to analyze relationships between variables, between parameters, for instance, the dependence of income on education, and you will learn about correlation and regression, which are the main topics when you want to analyze the relationships between two parameters, two variables. Then we have statistical reasoning. Actually, much of statistical reasoning depends on the theory of probability, and the connection is through chance models. And chance models, here we talk about coins, dice, and roulette wheels as the main examples of chance models. You will learn about expected value and standard error as the core concepts in statistical reasoning and probability. Also, we cover probability histograms, how to develop them, and how the convergence to the normal curve is relevant to statistical reasoning and analysis. Then we'll have inference, statistical inference, which is making valid generalization about a population from a sample. Okay, that's what we call inference. So you have a sample from a larger population, and then you want to generalize some conclusions, some facts about the population from what you see from the sample. This is the inference. We talk about estimation. For instance, how does the Gallup poll predict the vote in an election? And we will learn why are some methods for drawing samples better than others. We cover using chance models to analyze measurement errors. And also important is tests of significance, which is basically to judge whether samples are consistent with the hypothesis about the population. And you will see that statistical inference depends on chance models. If the model is wrong, the resulting inference may be quite wrong as well. So these are the core fundamental concept within the inference framework when we talk about statistics. So overall, remember we have two branches of statistics. Inference is the branch of statistics which is most interesting to professionals, and then we have descriptive statistics, which is also a very useful branch but easier to understand. So we cover descriptive statistics before inference. Okay, that was an overall outline for our series. In this episode, we review what we mean by designing a good experiment. Assume you have a new drug which is going to be introduced. The question is how to test the effectiveness of this drug. Does it really make any improvement in the patients? How effective it is? The basic method here is the method of comparison. So you give the drug to subjects in a treatment group, and other subjects are used as a control group, and then you compare the response of the patients, subjects that you observe from these two groups, and then you compare these responses from two groups. There are some well-established rules for a good design of experiment. A good design of experiment requires that the subjects are assigned to control and treatment group at random. So we talk about randomized controlled experiment. So controlled means you have two different groups, one treatment and controlled group, and the randomized part is how you decide which subjects belong to control group, which subjects belong to control group. And the idea is that you should make it completely randomized by pure chance, like flipping a coin, for example. The other important rule is that experiment should be double-blinded, which means that neither the subjects nor the doctors who measure the response know that they belong to treatment group or control group, because if they know, they might be biased about making measurements or doing the diagnostics about the effect of the drug. Okay, So that's why we call it double blind, because neither the subjects, the patients, nor the doctors who evaluate the response are aware of whether the subject, the patient, has received the drug or not received the drug, to eliminate the bias. So these ideas we will expand in the next few minutes. So let's start by a case study. It's a story of a real-world vaccine. We talk about the case of polio epidemic in the United States. The first epidemic hit in 1916 and claimed hundreds of thousands of victims in the next 40 years. So in response to that, several vaccines were developed by 1950. And one of those vaccines seemed most promising in the lab. It looked safe, and they could measure some antibodies against the virus. Okay, so that's why in 1954, the National Health Service was ready to try the vaccine in the real world. So you have an epidemic, several vaccines are developed, and then you see some good signs, some potential in the lab trials. Then you want to basically go and test the vaccine response in the real world before basically releasing the widespread use or approving the vaccine. So how do you basically do the real world trial? One way, the easiest way, which we call the poor design, uncontrolled experiment, we give the vaccine to a large number of kids, okay, and then monitor the number of incidents of the disease and compare them to the previous year, for example. If the number of incidents dropped compared to the previous year, then it might seem that the vaccine is effective. However, for epidemic disease like polio, the incidents vary year to year, and low incidence of a disease could mean two things. Okay, it was either vaccine was effective, or it could be that we are in a non-epidemic year, so you couldn't say that vaccine was effective. That's what's basically makes the uncontrolled experiments unreliable somehow. You cannot basically measure the effect of your change, the effect of your vaccine in this case. Okay, and what's the better way? There is another way of doing this experiment, and we call it, as introduced, is the method of comparison. So you deliberately leave some kids unvaccinated and use them as your control group, and then the others, they go to the treatment group and they get the vaccine, and then you compare the response from the control group to the response you see from the treatment group, and you then see if the treatment made any difference. So that's the only way to test the effectiveness of the vaccine. In the actual field trial, one thing to note is that treatment and control groups can be of a different size. Like it doesn't have to be equal, because you compare the rates of incidence in two groups in terms of case per 100,000, for example, and you look at the rates instead of absolute numbers of cases, and this adjusts for different in size. The experiment should be controlled. Okay, we learned that uncontrolled experiments cannot give you any meaningful indication of the effectiveness of the vaccine. So controlled experiment is good, but then the question is how you run this experiment. Okay, in controlled experiment you have treatment group, you have control group. The question is how you make these two groups. Okay, you have to decide who goes to treatment group, who goes to control group. One possible design is that you say, okay, the children whose parents consent to the vaccine, consent to to the treatment, You put them in the treatment group and they get the vaccine, and the other kids whose parents didn't consent to vaccination, you put them in the control group. Okay, so then you say this is a controlled experiment. But the problem is that this way you introduce bias against vaccination, and that's why this is a poor design of experiment. Why doing this sort of assignment we say is biased against vaccination? Because we know that higher income families are more likely to consent to vaccination, okay? And at the same time, higher income families usually live in a more hygienic environment, and as a result, they do not develop antibodies early in childhood. So as a result, we know that the kids, the subject in the treatment group, where the parents consented to the vaccine, because they are living in a more hygienic environment, they do not develop comparable antibodies to those who lived in a less hygienic environment. That's why they are more vulnerable. They are more vulnerable to the virus. Okay, so you have put subjects which are more vulnerable to the virus in your treatment group, and then you want to compare your treatment group to your control group. In these two groups, they are not similar. This is the bias, okay? And so comparing volunteers to non-volunteers here biases the experiment. That's why this is the poor design, better than uncontrolled, but still it's poor design. So the key statistical lesson is that treatment and control groups must be as similar as possible, okay, except only for the treatment, except only the factor that you are focusing on, which is in this case the response to the vaccine, okay? Otherwise, if other data, other factors are involved, then you definitely have a bias, as you see in this case. So the treatment group and control group are not equal in other factors. The family background changes the response to the vaccine, and you cannot judge from your observation whether the vaccine is effective or not. So this is the bias, and bias is not a good thing, so we call it poor design. So what can we do about it? Okay, another possible control design, which we call it a good design, is where you have no bias or have tried your best to minimize the bias. How you do that? So to avoid the bias, you have to avoid mixing family background effects, the hygiene effects, and every other things with the vaccine, with the effect of vaccination. So how we do this? We choose control and treatment group from the same population. The population will be, in this case, in the case of good design, the kids whose parents consented to the vaccination. Okay, so you first filter out your subjects based on the family consent, and then you have the population. So in this case, the population is all the kids, all the subjects who their parents basically consented to vaccination. So now in this case, you filter out the family background, the fact. Then the question is how to decide which of these kids go to the control and which of these kids go to the treatment group. One way is to just having the human judgment based on some relevant variables. For example, you look at the general health, how healthy they look, or personality, etc. And then you make sure that you make the control and treatment group as similar as possible. However, we know that from the experience, we know that human judgment always results in bias. So the best way is to rely on impersonal chance. And this is why we call it randomized controlled experiment. So controlled experiment can be randomized or non-randomized. Non-randomized controlled experiment we saw suffer from bias, and Randomized controlled experiments are those who which are basically offering the least amount of bias in your experiment, because you don't rely on human judgment, you rely on impersonal chance to assign subjects to your treatment and control group. So chance procedure in this case is equivalent to tossing of a coin for each subject, so if there is 50-50 chance that the subject goes to treatment or control group, and as you expect, such procedure is objective and impartial, so you eliminate bias by relying on chance procedure. And the law of chance guarantees that with enough subjects, your treatment and control groups are very similar with respect to all important variables, even though you don't know what are those variables. But by relying on the law of chance, you make sure that if you have enough number of subjects, then your treatment and control groups are identical, and you eliminate the bias. So when impartial chance procedure is used to assign treatment and control group, then we say the experiment is randomized controlled. So we call them randomized controlled experiments. Another point to consider here to avoid the bias in your experiment is to how evaluate the outcome of experiment. Okay, assume that you continue, you have eliminated the bias from the family background by doing the randomization. Then you observe the responses. You want to see whether vaccine was effective or not. Then you have to do the diagnostics, on the patients, on the kids. But the question is, if basically during the evaluation of the outcome of the experiment, in this case the epidemic, the vaccination case, you have to decide, did the subjects contract the virus during the experiment or not? The point is that if the doctors knew that the subject got the vaccine or not, if they were aware of whether the subjects got the vaccine or not, it's most likely affects their diagnostics, their judgment of whether the vaccine was effective or not. It affects their measurement of the impact. So that's the double blinding. So you make sure that the subjects do not know whether they belong to the treatment or control group, and also the evaluators also don't know whether each subject is coming from treatment or or a control group. So this is the idea of double blinding. So the best possible design of experiment is randomized controlled double blind experiments. Okay, randomized controlled double blind. By doing so, you minimize the bias in your study, in your experiment, and the rule is that we should aim to use this framework wherever it's possible. Okay, now let's see in our vaccination case study, how did it go? How did it all turn out? What was the result? So in this table, you see the rate of polio disease cases per 100,000 subjects for treatment group, for the vaccinated group, and for control group. What you see here is that both randomized control experiment and poor control experiment, which was biased, the rate is much lower for the treatment group compared to the control group, and this shows as a proof for effectiveness of the vaccine. Okay, because this is obvious that the rate of incidence, polio cases, the disease cases for the vaccinated group is lower compared to the control group, both in poor design and in good design. However, there is something to note here. In randomized control experiment, the vaccine cut the disease rate from 71 to 28 per 100,000. And in the poor controlled study, in the poorly controlled experiment, the reduction is from 54 to 25. So it is basically, it's showing less effective. It's still showing some effect, some positive, but it's less prominent. And the reason, as we saw, is that in a poor control design, we have bias, and the main source of the bias was the mixing up of the effect from the family. Family background mixes with the vaccine effect, and control group in the poorly designed experiment was not comparable to the control group. Remember, for the poor experiment, for the poor design, you assigned treatment and control group based on the parental consent, and when you do this, the subjects who go to the control, they are more resilient, and as a result, the number of incidents in the control group turns out to be lower compared to the good design. Okay, and this is the bias. So you have this. The effect is diluted. The effect of vaccine is not clearly visible in the poor design. So we saw that randomized controlled double-blind experiment reduces the bias to the minimum. However, it also offers another key technical advantage. Let's assume in our case study of the polio vaccine, let's assume that the vaccine had no effect. So we call it, in statistical terms, a null hypothesis. So you play devil's advocate. You say, let's assume vaccine has no effect. Then, as a result of this assumption, you logically conclude that under this assumption, the difference between rates of disease for the treatment and control group is just due to the chance, okay? Because you assume the vaccine has no effect. Then any difference you see between treatment and control group in a well-controlled experiment should be only due to pure chance. How likely is that? With poor design of experiment, there is no enough information to figure this chance. But with randomized controlled experiment, on the other hand, the chance enters in a planned way when you assign the subjects to treatment. So this is a very key technical advantage of a randomized controlled experiment, because you can calculate the likelihood, the likelihood of getting the result that you observe, the difference between two groups, and then you assume there is no effect, and then you calculate how likely it is that you see this observed difference. The null hypothesis says that vaccine has no effect. So on this hypothesis, a few people are fated to get the virus just by pure chance. Whether they are assigned to the control or treatment group has nothing to do has nothing to do with it. It's just by random chance variation under the null hypothesis, okay? So each subject has 50-50 chance to end up in the treatment group and get the vaccine, or ended up in the control group based on just flip of the coin. And also each disease case has 50-50 chance to be seen in the treatment group or in the control group. Therefore, number of cases in two groups, number of disease cases that you see in treatment group and in control group must be about almost the same. And any difference you see between the number of cases in these two groups is due to chance variation, which is introduced in your flip of the coin process when you assign the subjects to the groups. Okay, this is very technically important in statistics, and in our final episodes of this series, you will see how significant it is, in drawing conclusions about experiments and tests of significance and the practical aspect of this. But the whole process is like this. You have a null hypothesis, basically how likely it is that you see the difference between treatment and control group, and statistics addresses this variability and to figure the probability of seeing a difference as large as the observed difference. So we get to this topic in future episodes when we get to the inference, statistical inference, and the tests of significance. Okay, as a second case study, let's see why good design of experiment is critical. We are looking at a case where some studies were done to conclude the effectiveness of a treatment via medical surgery. So this is the real world case from the medicine. So 51 studies were done separately by different researchers to assess the effect of surgery. And basically researchers studied all these studies, and they classified them. Some were poorly designed, some were well designed, and what is evident, they conclude that you will see that well-designed studies, well-designed experiment, which are controlled, randomized, double-blind, shows surgery have little or no value. Okay, so you put yourself under the surgery, you put the patient under the surgery, and all the risks coming with it, but the actual value is non-existent, basically is zero. But when you look at the poorly designed studies, the poor experiment, which were either uncontrolled or controlled but poorly controlled, including bias, those poorly designed studies actually exaggerated the value of the surgery. Okay, so in this case, 32 studies were performed without controls, and 75% of these studies said that the surgery is remarkably positive. So there were 75% of these studies were quite enthusiastic about the results of the surgery. If you look at those studies who were controlled, but poorly controlled with bias, the assignment to the treatment and control were not randomized, you see that 67% of these studies showed positive about results. So the more, as you improve the quality of experiment, you see the different conclusions from the studies. So in the poorly designed experiment, you have the patient population. In those studies, the healthier patients went to the surgery group, and the sicker one went assigned to the control group. And because it was not randomized, you learn that you should not expect that you see a real conclusion from these studies, because it's not fully randomized, properly randomized. But there were some studies that were randomized, controlled, and those studies showed little to no value of the surgery. And how they were done? So they were done in a way that you first have a patient population. You first filter out eligible patients, those who were not too sick or they didn't consent to the surgery. So you have these eligible patients, and then from this population, you choose, some go to treatment group, some go to the control group, and the way you do it is by a randomized chance process, as we discussed previously. You randomize eligible patients into treatment or control without any human judgment, and in that way you have a fully randomized controlled experiment without any bias. And in this case, you see no value of the surgery. You can see how the quality of experiment affects the judgment of affect the conclusion about what an experiment. And the lesson in this case study is that, in this case, a poorly designed experiment exaggerated the effectiveness of the treatment. You might ask how they measured the result or how they concluded the effectiveness. The answer is that they looked at the 3-year survival data. Okay, for well-designed randomized experiments, 3 years survival for the treatment and control is equal. So 60% in the surgery in the treatment group survived after 3 years, and the same is for the control group who didn't do the surgery. It was the same rate, 60% survival, 3-year survival. That's why they concluded there is no value. But in the poor design of the experiment, they didn't do the randomization. Only 45% of the controls survived for 3 years, compared to the 60% of the patients who were in the treatment group. And based on this observation, they concluded that the surgery was positive. Okay, so it looked to them that the surgery was effective, but this was bias at work in favor of the surgery, because the sicker patients in the non-randomized case were put in the control group. And when you put the sicker patient in the control group, obviously the 3-year survival is comparably less compared to the treatment group. And you have another diluting factor in your experiment that basically mixes up with the effect of the treatment, effect of the surgery. And because you have the bias, because you have the sicker patient in your control group, you see the survival, 3-year survival data for your control group less than for your treatment group. And you see, you may conclude that the surgery was effective, but practically, judging from the well-designed experiment, the conclusion is that there is no effect, there is no value in doing the surgery. Okay, so this was the case study number 2 to show you why good design of the experiment is critical. Then, as a third case study, we have the case of DS tragedy, to emphasize that the good design of experiment is super important, and if not followed, can be catastrophic. The point is that sometimes the randomized experiments are hard to do. In the case of DES, what happened is that they used historical controls, and historical controls means that they used patients treated the old way in the past as control group, okay, and compared those to patients who got the DES in the treatment group. And the problem is that when you use the historical control, might differ in important ways that makes the study biased. And this is what happened for the DES case. The result was a medical disaster. And doctors basically missed and ignored the randomized evidence. Randomized trials showed no effect of DES, and some of them even indicated that the risk of the cancer side effect. And but the doctors at the time relied on the historical controls, and all those historical studies showed positive results. But then it became evident that all those studies, they were biased by the era improvement. In 1970, it was discovered that DES causes cancer. Also in the next generations. In 1971, FDA banned DES, but thousands already affected with cancer, infertility, and birth defects. So the important lesson is that the good design of experiment is not optional. If you want reliable conclusion from your experiment, from your data, you have to make sure that your experiment is properly controlled and randomized to minimize the bias.